Please welcome Arman Zaribafiyan, CEO of Good Chemistry, for a discussion on the integration of Tangelo and Qiskit Runtime.
Well, thank you so much, Jamie, for that amazing introduction. Hello, everyone. I'm grateful to be here today to tell you a little bit more about how we are leveraging IBM's quantum technology with some of the software that we have developed on the cloud for computational chemistry, like Chemist Cloud and Tangelo, to build an end-to-end workflow for computational chemistry and use that to a sneak peek at what the future of materials innovation could look like. But before doing that, let me tell you a little bit about who Good Chemistry is. We are a material science software startup based in Vancouver, BC, but we're distributed with more than 30 machine learning engineers, cloud architects, and computational chemists. And we are gathered together, and our mission is to make the world cleaner, healthier, and more sustainable through accelerating materials design. Why are we so excited about this mission, though? The reason is that we truly believe some of the most challenging problems that humanity faces right now has solutions that are bottlenecked by our ability to build better materials faster and cheaper. Climate change, renewable sources of energy, building better electric vehicle batteries and energy storage solutions, carbon capture, drug discovery are all examples of that. But bringing a new material to market is a difficult problem. Nothing better exemplifies that than this example that I have here. If you notice, the number of possible synthesizable molecules dwarfs the number of particles in the observable universe. We are dealing with a huge search space, and that means that we truly are facing a needle in a haystack problem when we want to bring a new material to market. So at Good Chemistry, we are trying to change that by building essentially a supercomputer for chemistry on the cloud. Chemist Cloud is our platform that provides high throughput, high accuracy chemistry simulations as a service. And it's really simple. The input is representations of molecules, and the output is basically the platform spinning up millions of cores on the cloud to be able to provide rapid simulation and prediction of their chemical properties. This platform is already released in private beta and serving enterprise and academic users from different industry verticals right now. The core of Chemist Cloud is machine learning. And are machine learning-driven, highly efficient quantum chemistry tools that are able to predict material properties at a scale. Let me show you what we are able to achieve with this. For example, we have this machine learning engine that is able to provide geometry optimization, which is one of the frequently used workflows in material simulation, 100 times faster than a state-of-the-art. But the problem is that machine learning models are only as accurate as the data that they receive. And that's why we have this other second component in Chemist Cloud that uses cloud-native algorithms to run massively parallel quantum chemistry simulations at a scale. And just to give you an example of that, we recently were able to use that on the cloud to break the record of the largest simulation ever running on a computer to FCI accuracy, to exact accuracy of a molecule, basically. We simulated decasene with more than 200 electrons and 600 orbitals in less than 11 hours and with using less than $2,000 in cloud credits. That's the record of the largest molecule ever simulated. And we believe that even though that's impressive, but it's not enough. In order to be able to facilitate and accelerate searching that search space that we just referred to, we need to be able to do more. And that's why we are excited about the potential of quantum computing for material simulation. Because essentially a combination of quantum and classical computers would be able to provide larger scale, high accuracy data for training these machine learning models. So that's the reason that since the inception of Good Chemistry, we have been working with Dow, which is one of the largest advanced material science companies in the world, on exploring exactly that. How can we leverage quantum computers to accelerate simulation of organometallic catalyst? As you can imagine on the picture on the right-hand side, Dow is not impressed by simulating the hydrogen molecule. They want to be able to see a simulation of that beast over there, which is, by the way, one of their organometallic catalysts, a constraint geometry catalyst. So very early in the game, we started focusing on how we can bridge the gap between where quantum computing sits now and what the industry needs to be able to simulate this. Therefore, we focused on problem decomposition ideas, ideas that can take a complex chemistry simulation, shatter it into pieces that are independent, and to be able to use fewer resources to be able to calculate these larger experiments and do more with less, basically, in parallel. One of the methods that we developed with them is the method of increments that is based on a many-body expansion, and we have published a number of papers on this topic to describe the theory of it. But over these 5 years, we also put together a robust software stack that we used to be able to run these end-to-end computational chemistry workflows on quantum computers. And I'm very excited today to announce that this software stack called Tangelo is open source and is available for everyone to use. Tangelo provides end-to-end chemistry workflows, and basically it's able to take a molecular system representation, provide those unique problem decomposition solutions that are specific to chemistry, and then gives users a lot of freedom in terms of how they build quantum algorithms and quantum circuits, and to be able to connect with real quantum computers to solve those. Now, the interesting point is that this is where we relied on IBM's Qiskit runtime. And I think the team at IBM has done a phenomenal job in streamlining the process of running these experiments on a quantum computer, that we can basically not worry about what's happening when we submit a problem to a quantum computer and just focus on the application layer, basically what we know best, which is chemistry. So today, I'm actually really excited to show you how this end-to-end workflow is coming together, and we are taking Chemist Cloud, Tangelo, and IBM's Qiskit runtime and a real IBM hardware together to build an interesting experiment that uses this idea of problem decomposition to go beyond what's possible today on quantum computers. So as an example, we are starting with a beryllium isoelectronic series problem. This is in a sophisticated basis, basically CCPV-DZ basis for people who are a little bit more familiar with this space. And the important takeaway here is that in this example, shown in the standard representation, this is a problem that requires more than 25 qubits and more than 7,000 gates to be able to simulate it. Now, we're going to send this problem to Chemist Cloud using the method of increments that I introduced earlier to decompose this into independent smaller pieces, and then use Tangelo to turn these pieces into quantum programs. And we see that now we end up with problems that only need 2 to 4 qubits and less than 10 gates per those circuits. Then the magic begins. We're going to connect Tangelo to Qiskit runtime, use the efficient estimator primitive and also the streamlined job API to be able to send all of these requests in parallel to an IBM hardware. I believe we use the IBM Quantum Calcutta device to be able to get the results back, post-process it, and then see if we can aggregate the result of that larger problem that we have started with. So let me show you this in a clip that I have recorded of the experiment. So as you can see, this is Chemist Cloud's dashboard. We have submitted the problem. We can see all the parameters of the setup of the experiment, the molecule that we have, and information about the experimental setup, the basis set, and all of the other components. And very easily, through a simple Python API, we are able to retrieve this information from the cloud and to look at all the fragments that were generated through method of increments, and then to use the functionality that exists in Tangelo to turn those fragments into quantum programs. And here we used, I believe, a version of adapt VQE, for example, as the quantum algorithm, and we set up the operator pool for it. And using Tangelo, we are able to compile this circuit that is much simpler than the original problem we started with. And now this is really interesting. Look at how simple it is to turn these circuits and send it to IBM Quantum using Qiskit Runtime. And you get this nice dashboard here where you can see how your job is progressing. And the interesting thing that we went over it really fast. The total experiment time took 4 minutes, which is really interesting. But we were waiting 14 hours in line to be able to get that. And I think that's really impressive. I was talking to one of my colleagues, and he said, you never want to eat in a restaurant that is empty. The fact that we are waiting in line to run a 4-minute experiment means that there's an incredible community behind this, and there's a lot of requests to run interesting experiments and exciting explorations with this platform. So this is really exciting. Now we are able to retrieve the result, again, through a simple Python API, and to be able to post-process it. And now I'm going to show you why some of these post-processing and error mitigation and error suppression techniques that was introduced earlier is really, really important for these workflows to work. So this is the raw result that we get from the hardware. This is, by the way, an energy scale for the BE isoelectronic system that we looked at. The starting point is near Hartree-Fock energy, and this is really cool that we are able to get that on the quantum hardware. Not quite near the exact solution, though. But look what happens when we apply readout error mitigation available through Qiskit Runtime. We are much closer to the accuracy band around the exact solution. And then this is where some of the presentations before talked about zero noise error mitigation that is unique to Qiskit Runtime. This is what happens next. When we apply this sophisticated error suppression technique, we are in the exact band. So let's review what happened. We took a problem that needed resources beyond what is available today. We broke it down into smaller pieces. We compiled those smaller pieces into a series of small quantum circuits and used the streamlined job API within Qiskit Runtime to send them to a quantum hardware, got the result back, and then we post-processed it, and now we got the result to the original solution within chemical accuracy of the exact answer that we were expecting. So hopefully I have shown you how we can put together computational chemistry workflows with what quantum computing is offering to generate high accuracy data for materials discovery at a scale. I want to finish my talk by basically saying these platforms are now available, and you can learn more about it from our website, goodchemistry.com. And Tangelo is also open source and available for you to test it for yourself through Qiskit Runtime as well. Thank you so much for listening to this presentation.